on air.
אוקיי.
היה לי את הקטע הזה.
זה קשור למודל אייסינג, תקשיב.
באמת?
קשור למה?
It's talking about the icing model, so I told you.
Yeah, it's closely related to the icing model. No, Ethan sent me your
Oh, yeah, sure.
notebook.
Yeah.
Okay, so Shai needs to do a couple of changes to his notebook, so we will hear him next week, and we start today with time series analysis. Okay, first part. What do you think is behind this time series? You know already, so don't say it. Maybe you forgot.
Like the function?
I mean, time series, everybody knows what is a time series, right? I don't need to, maybe I have to say what is a time series. So, when you measure something over time, it's a time series, okay? You go to the lab and you measure, what is a good example? You measure the magnetization in the icing model over time, okay? By changing the external magnetic field, typically. Is this a good example? This way you get a time series, right? You get the overall magnetization over time. This doesn't look like magnetization over time. What could this be? What is measured here?
Global temperature?
Temperature, okay, temperature
Maybe
is good.
some harmonic oscillator?
Hmm?
Harmonic oscillator?
Harmonic oscillator is also good. Harmonic oscillator.
That's falling down.
Why do you think it's a harmonic oscillator?
Because of the oscillation.
Because you have oscillation, right? Why should it go up, the harmonic oscillator?
Maybe it's falling down as it goes. Like a spring? Yeah, that's falling off the building.
But the spring is part of the harmonic oscillator, no?
Yeah, no, but I'm just thinking why it goes up.
Why it goes up, yeah.
I don't
You need something
know.
that pushes it up, right? You need some external force, so to say. The temperature, Joseph, is also not bad. Why temperature?
Because global warming, so the temperature.
Oh, yeah. Yes, you have an overall increase because of global warming, right?
Yeah.
And you have an oscillation because of what?
The temperature is not stable.
Hmm?
It's not so stable.
No, it's not stable, it's the seasons, right?
Yeah.
But you could also see another oscillation here, which is for temperature.
Time of day?
Yes, day and night. It's also different, right? Depending on where you are, it's larger or smaller amplitude. So in fact, this is how you basically intuitively understand time series, right? And this example here is actually taken from the Mauna Loa in Hawaii, and it is measuring the carbon dioxide, okay? So carbon dioxide from the 60s until the 2010, it is increasing over time. They say there is a critical threshold at 500 parts per million for this kipping points that you hear maybe in the news. In these climate models, you have kipping points that once you reach this kipping point, you get some irreversibility in the models, right? So this reaches here 380, and then you have here the annual cycle. When you zoom in, you see there is an increase in the spring, a decrease over the summer, and then it increases again in fall. Why? What do
Tourists?
tourists?
Yeah, more tourists.
A lot of tourists there, they are breathing, and then they have a lot of good.
No, but the more cars are being driven on
More
roads.
cars. Good point, yeah. Actually, it turns out it's the plants, okay?
Plants?
So, yeah, because you have more. So, effectively, in the.
But isn't Hawaii sunny all the time?
Yeah, but still, you have a difference in the. You're right, when you go to the equator, to the rainforest in the equator, you will not see this, right? You need to be off the equator, that you have a difference in photosynthesis efficiency between spring, summer, fall, and winter, right? So this is what you see here. Good. So how would we analyze this, right? I mean, the subject of the course is time series, of the class is time series analysis. How would we analyze this? Exactly, intuitively, what you already looked at before, right? You say there is a overall trend, right? So this is my time series. There's an overall trend. It's not linear, it's some polynomial, right? Maybe quadratic, something like this. So you can just take this out of the data, right? You subtract this from the data, and what you're left is this residuals. This is basically what is fluctuating on top of this trend. What would be the next step to dissect these residuals? What would you do?
Fourier transform?
Yeah, but good, but colloquial. I mean, Fourier transform does what?
Sees the frequencies inside.
Yes, you want to take out the periodic trend, right? You do a Fourier transform in order to identify the dominant frequency. Then you would bandpass filter the signal basically, and you would get the residuals again. So you have here the annual cycle that you take out. Okay, it's some average annual cycle. It's a periodic trend, and we are left again with some fluctuations on top of this annual cycle. Okay, this was not so much visible here in the previous. I mean, you could see, right? I mean, if it was strictly a trend, you would have all the time the same envelope. I mean, the envelope would be constant, so to say. But here you see fluctuations, right, in the amplitude. And this is because of these fluctuations. So the question of the first part of the talk is whether this contains any useful information or it is just noise. Okay? Good. Why is this important? Because if you look at time series, here's an example. You have a temperature time series from Prague in Czech Republic. You have here river levels of a river in Germany, and you have here the heart rate, basically. I mean, this is the inverse of the heart rate. It's time intervals between two heartbeats, so to say. And I colored here everything that is above the mean in red and below the mean in blue, right? And you see that you have this noise, right? It looks very noisy. It's the residuals that I just showed you before. I mean, here I kept the periodic trend, or here it is everything above simply the average, right? But we are talking about these clusters here. I mean, you see, it is something that is not random. If it was random, you would not see this kind of clusters, right? And here you have large, so this means you have the river was much lower, the river level was much lower over a couple of days than in other years, right? And here you had a kind of flooding, right? And also here. And for the heart rate, this is over the whole night. You can see here even sleep stages, right? I mean, when is your heart rate? So first of all, blue is an elevated heart rate or a lower heart rate. Just this time intervals between heartbeats. What would blue be? Lower or faster heart rate? No? Lower, right? Because you have a longer distance between the heartbeats means lower heart rate. So when you have blue here, this means your heart is beating slower, and in red it's faster. And what you see here basically is, anyone can guess what are these red areas here?
REM sleep.
Yeah, it's REM and wake. Okay, so both of them have elevated heart rate. So here you have short awakenings. This is REM sleep. These are short awakenings. Then you have again REM sleep, and perhaps cannot say because I don't see the just from the heart rate. It's difficult to say. But if you would look at the EEG, maybe you would identify this as REM sleep again, and here awakenings, and again REM sleep, and you see that REM sleep increases over the night, right? In the beginning of the night you have short epochs of REM sleep, and the longer you sleep, the longer get these epochs of REM sleep. And deep sleep, the opposite. First they have long epochs of deep sleep, and overnight they get shorter and shorter. So important to understand this clustering, this kind of residuals. Is there any information in them? And in order to determine whether there is information, we do now a comparison that at the beginning looks a little bit far-fetched, but we will see that it's very useful. It turns out to be very useful, and this is the following. When we talked about percolation cluster, right, the percolation cluster, we also said the percolation cluster is a fractal, right? When is the percolation cluster a fractal? Two things you should...
the critical...
At criticality, exactly at criticality, it's a fractal at all length scales, and when you are above criticality, it is a fractal only when you are below the population length, right? You have to zoom in, and then it becomes a fractal. You remember we did this in class. So here, this is the percolation cluster at criticality, and you remember what we did was we zoomed in, and we saw all the time the same picture. And what we could do is we could calculate a fractal dimension, right? df. This is simply what last week Ethan was telling us again, box counting, right? You take bigger or smaller boxes, and you see how, in this case, the mass changes with the size of the boxes. Good. Now we are here confronted with the problem that we have a time series, and the time series, when we just would zoom in with a box, right, with a square, more exact is to call it a square. When we zoom in with a square, we would not retain a similar picture, a self-similar picture. What we have to do with time series is we have to zoom in with a rectangular. Okay, so what you have here is a time series on top over 640 seconds of blood perfusion in the brain measured by Doppler ultrasound, and the blood is fluctuating. Okay, blood is fluctuating, and what you do now is you zoom in. You zoom into the beginning of this time series, but not with a square as we did for the calculation cluster, but with a rectangular. So you have a different length in the y direction than you have in the x direction. If you do this, you recover a picture that looks very similar, right, to this one. Again, if I would ask you at which time, at which scale this time series was taken and this time series was taken, we would not be able to tell. Okay, this is exactly what we said as a definition of a fractal. So this is a kind of a fractal in time. Okay, and you can do again the same until a certain level. Then, of course, the signal becomes so smooth that you can see at which scale you're measuring. So we want to basically get a measure now that is similar to the fractal dimension that we obtained for the calculation cluster, for example, for this kind of time series, right? So how can we do this? And let's follow perhaps the same ideas as we did when we talked about the fractal dimension, and see how we can improve these ideas to fit our problem. You remember the Sierpinski triangle from last week? We had here simply when we increased the x dimension by a factor of 2, also the y dimension increased by a factor of 2, right? Good, but here we have now something anisotropic. So let's take a generated artificial time series according to the following mechanism, that every time we have a line up, okay, we replace this line up by this hook, okay? And every time we have a line down, we replace it by this inverse hook, so to say. And then in the next iteration, so we are now here, we have a line up, and we would replace it by a hook, okay? So we are here. Now we would have a line down, and we replace it by a hook like this, okay, inverse hook. Then we are going up again, so we are replacing this by a hook this kind, and we are going up again, and we replace it by the same hook, right? Everybody understands how this is done? And if you do this in the next iteration, it gets more and more ugly, right? But looks a little bit like a time series, right? But we can understand, we have exactly now the rule how to generate this time series. So and now let's follow the same ideas as we did for the fractals, and think about how let's say the mass of such an object, M, scales with the length in x direction and the length in y direction, right? And what you see here is when you take 4 units, right? We did this 1, 2, 3, 4 times in x direction, right? By how much did y grow? So x grew by a factor of 4, right? We had 4 of these units. How did y grow? You can see it there. Factor of 2, right? Factor of 2. So this means x, it's even written here, by a factor of 4, y by a factor of 2. So that means if I would take the fourth of the length in x and half of the length in y, I would recover 1/4 of this object, right? 1/4 of this object. So this is written here. Good. Now let's compare this to our formula that we have for the box counting. MEL is equal to B to the power of df times ML. What's the problem? Just compare the two.
That it's different scales for x and y.
Exactly. Okay, so you have here only one parameter, and you have here Lx and Ly. How could we solve it? What would you do?
2 different parameters, and you multiply by both.
Yeah, or connect the two, right?
Yeah.
So you could say, I need to find a measure that connects the two, and then I use this one measure instead of the two. So what would this be? Perhaps I could take the arithmetic mean. I could say it's the square root of 8, right? I replace this by square root of 8. So my B would be square root of 8. It's 4
That's the
times
arithmetic
2.
mean.
Hmm?
That's the geometric mean.
Geometric mean, yes. Arithmetic would be adding up. Yes. So square root of 8 would be an option, and then you could save this, and then you could just do the kind of box counting idea, and you would reach to a factor dimension, right? It was done like this, but it turns out to be a little bit more cumbersome and complicated. Therefore, people had a different idea what to do. And what did we do in order to find this one parameter? We combine x and y, right? So we can also just from the beginning look at a measure or take an alternative definition of dimension, and we say, okay, we look how my length in x direction scales with my width. So this cut should be a W, my width in y direction. Okay? So why not to do this from the beginning? Okay? And then we say, okay, then I have just a W for y direction and an L for x direction, and I have only one parameter, B, okay, that we had before. However, this is not now the fractal dimension as we had before, but something else, and it's called, this exponent is called alpha, and the is something like, giving you something like the roughness of the time series. So it's the roughness exponent, and then you can just easily plug in the numbers, right? You said before in the x direction scales by a factor of 2, the y direction by a factor of 2. You plug it in. B has to be equal to 1 over 4, and when is 1 over 4 to the power alpha equal to 1/2 if you take a square root, right? So alpha is equal to 1/2. So you get a roughness exponent. That somehow is a substitute for the fractal dimension. Another example, now you have something, instead of going up 2 units, you go up 3 units, okay? With this idea that we just learned, you can just plug it in. So instead of going up 4 units, you go up 5 units, so it has to be 1/5. And here it is 1, 2, and 3 units in x direction. Okay, so it's 1/3, 1/5 to the power alpha, and you get here log 3 divided by log 5, it's 0.68, okay, as a roughness exponent. So you see, the higher the alpha, the more, it's a roughness exponent, so the more rough or the more smooth. If you just compare this to this.
It looks smoother.
Smoother. Higher alpha, smoother curve, right? Higher alpha, smoother curve. And just to give you the idea of what would have happened when you did follow the thoughts we had in the beginning with the fractal dimension, and you take this geometric mean and you do all the box counting approach, then you would get the df, the fractal dimension, and the relationship between df and alpha is that df is 2 minus alpha, okay, in 2D. It would be another 2 slides to show this mathematically, but it's more important for me that you get the intuition, okay? And in time series, people use alpha instead of df. For fractals, they use df, of course, it's more natural, but for time series, they use alpha, because for alpha, we have all the methods to calculate alpha, okay? Easily. Good, so let's, after we develop this kind of intuition, let's look at a couple of examples. We said, okay, alpha is the roughness exponent. It's also called H capital. In some books you find instead of alpha H capital, because the one that suggested the first method to determine alpha is Erwin Hurst. Okay, we will talk about him in a bit. But it's basically the same. Alpha and H is the same, more or less. And here are some examples. So if you take just your random number generator from Python or MATLAB or whatever, and you say you want to have random numbers, right? What do you get? You get Gaussian noise, right? Gaussian noise, stationary Gaussian noise has the same mean of 0, okay, when you take it from the normal distribution, and also the same variance everywhere, depending on what you chose when you generated your numbers. So this is a stationary signal. If you would calculate your roughness exponent, it's 0.5. So we already learned roughness exponent 0.5 means random signal, right? Now you can just integrate the signal, then you get a Brownian motion, non-stationary Brownian motion, and this looks like this, okay? Looks like this. When you do an integral, then of course you add 1 and your alpha is 1.5, okay? And now it's non-stationary. You see that the mean of this signal changes all the time, and so does the variance, right? Good. So now let's look at a couple of examples of the Hurst exponent. And Ethan, you're right. If you look at, you can generate different signals, Gaussian noise signals. This is just random Gaussian noise, but you can also do anti-correlated Gaussian noise and positively correlated Gaussian noise. And here you see that if you have something with a Hurst exponent or alpha of 0.1, it looks more rough signal, right? Even when you integrate it, integration should usually make it more smooth. It makes it a little bit more smooth, but it still looks very rough, right? When you go to something with a Hurst exponent of 0.9 or alpha 0.9, you have something that looks more smooth, and when you integrate it, it looks even smoother, right? So here you see what we just said before. If alpha or h is larger, it means our curve, our time series, looks more smooth, okay? Less rough. So here's the summary. If you're between 0 and 5, it's anti-correlated. So anti-correlation means that you have a process. So when you have anti-correlations and also these positive correlations, it means your process has a memory, okay? So anti-correlated signals have a memory from a feedback, usually negative feedback. An example would be a thermostat, okay? You try to keep the water temperature at exactly the same temperature. The water at the same temperature. So you would you measure the temperature, and when you are above the temperature, you switch off your heating, right? And then it goes down, the temperature of the water, and then you heat it up again, right? So you have a feedback inside, and this leads to a anti-correlated signal. Yeah.
So it depends only on the last sort of output.
No,
on everything.
You can do it. It depends on the. Usually they have a memory over. It depends. You have to calculate. I mean, you can calculate how long is the memory, so to say. Okay.
So why is it still called random?
No, it's not random. Random is only when it's 0.5. When it's anti-correlated, you have a memory. It's not random anymore. Okay. It's not random. If so, Brownian motion is random, as you know from physics, right? From thermodynamics, Brownian motion is random. A positively correlated process is also not random, but here we have a different phenomena, and again, a process behind that wants to keep the status quo, so to say. So an example is weather data. Okay, so it is more likely that today you have a similar temperature than yesterday. Okay, it's very unlikely that the weather is completely anti-correlated. Okay, you have freezing temperature one day and very hot temperature the other day. It's not anti-correlated, it's usually smooth, and you have a persistence in the data. Why do we have positive correlation in the data, in the temperature data? Somebody has an idea?
Because the weather doesn't change that fast.
Why? How is temperature? What causes temperature, so to say?
The heat from the sun, mostly, and the cloudiness.
Yeah, you have high pressure and low pressure areas, right? If you look at satellite images, you have high and low pressure areas. This is what they show usually in the news, and they tell you about how the weather is going to be the next couple of days. They show some high pressure area, and the high pressure area is big usually, right? It's about it's Israel and the Mediterranean and Egypt combined, right? And then it moves slowly, right? So this makes the long-term correlations or the positive correlations in temperature, because you're sitting in some area and the high pressure field is moving over your head, but slowly. So the temperature tomorrow will be similar than today. Only when the high pressure field is finished, you know, and you have a low pressure field, then you get rain. But then again, it stays low temperature again for a couple of days, because the low pressure field has a dimension. Okay, so that's but you get a feeling why it is important to identify whether you have anti-correlations or positive correlations in the data. Again, so we are talking about this, right? I mean, the trends and the periodicities, they are trivial. We are talking about this and whether we have useful information. And I told you that the exponent is also called Hurst exponent, because Erwin Hurst was the first to suggest a method to calculate this alpha, this exponent, or h, right? And how did he get confronted with the problem? It happened when he was tasked by, at this time, the British government to design or to calculate how high the Aswan Dam in Egypt has to be built that it will not overflow. Okay, so we remember the Aswan Dam is here. It's up the river Nilus. They had to move a whole, I think, they moved a lot of pyramids and stuff. How is it called, the area that they evacuated, because it was flooded afterwards by the dam?
Memphis.
Memphis? Memphis is in the US, no?
No, it's also in the.
There's also Memphis there?
Yeah, it's where all the tombs of pharaohs are found.
Maybe, but it's called has a different name. I forgot. But all this, there were a lot of graves also there, and they had to move everything away from the place that got flooded. So anyway, he had to. So in the end, look, it is 550 kilometers long. Quite. I mean, it's like Israel. So it's like a little Israel as a lake. You can imagine. Good. So how did he approach the problem? He said, okay, let's do a couple of assumptions. Okay, and the assumption is that the
or maybe Nubia.
Nubia, no, it was called different. Maybe Nubia was part of it, yeah.
Nile River.
Yeah, it was. I forgot.
Okay.
But it's.
ChatGPT told me Nubia.
Yeah, but Nubia, maybe Nubia. But so how are the graves called there? Abu Simbel. Abu Simbel was evacuated. Abu Simbel. Yeah. Abu Simbel. Maybe Nubia is part of Abu Simbel. But it was a big thing in the 50s. Yes, so the criteria apply to the dam, to the lake there, as assuming that it's an ideal reservoir. What is an ideal reservoir? That you have the outflow of the dam is uniform. Okay, you can imagine everything that, so what goes out of the dam is it's just a constant flow. Then the level is the same at the beginning and at the end of the observation. Okay, and the reservoir never overflows. I mean, this was the condition, right? It should not overflow. So, and now the Egyptians have a record for many years over the water levels of the Nilus. Why? Because their life depends on it, right? We know this from the story of Joseph, that Egypt lives by the nihilus. Maybe now not so much anymore, but at earlier times it was very important for them to keep track. So they have the water levels xi, and the water levels xi are proportional to the velocity of the water inflow to the dam, right? It's obvious. So here you have the xi over a period of time, and they fluctuate. They are like what we talked about before, this Gaussian noise signal. Maybe with correlations, maybe not with correlations, but it's a stationary signal, more or less, right? Then the next, he says, uniform outflow is the mean of the inflow. So I have varying inflow, but we said the outflow is constant, and it's the mean basically over all the inflow. I mean, what comes in needs to go out, right? So, and then you can calculate from this a bit of the increase in water volume of the dam, which is given by the sum of the difference in inflow and outflow. So you have here the inflow, here you have the averaged outflow times delta t, and this gives you the height of the water level, right? And then, so this is the height of the water level, and then you just take the maximum minus the minimum, and this should be the height of your dam, basically. So this is what he said. And as a bonus, he saw, okay, now when I do, I put this R and this S into a relationship. This is exactly the same idea that we had before, right? We wanted to know how much Y grows as a function of X, right? So here it's R, which is the height of the water level, the difference of the height and water level, and S is here the standard deviation, but it doesn't matter. But when you put these two into a relationship, R over S, it scales like the time, so N is the time window of observation, to a exponent H, or alpha, okay? So this was his idea, and the first time that somebody could numerically calculate the roughness exponent. So nowadays we do it a little bit more, I don't know if elegant, but easier with getting the same results. We call this fluctuation analysis, but it follows the same idea as the Hurst analysis. We say, okay, the water level is the xi, right? And we calculate a profile. We just integrate the this is also what Hurst did. He just did an integral. He summed up all the xi, so you get something like this, right? The blue line here is this profile, the integral over the xi. You can remove the mean, but you don't need to remove the mean. And then you divide it into these windows of observation S, and you calculate just the difference between the beginning and the end of this window, right? Beginning and the end, all the red circles, and this gives you your kind of fluctuations in this window, f1, f2, f3 until fk. You square them and you average. Okay, so it's you do, if you have k of these windows, you average them, and you take a square root, and then you get a typical fluctuation for this window size. Okay, and then you repeat it with larger s and larger s and larger s, and you get for each of them an f of s, and you plot now f of s versus s, so the fluctuations versus the scale of observation, and this scales with the time of the window of observation and an exponent alpha, and when the alpha is between 0 and 0.5, it's anticorrelated, the same thing as before, random when it's 0.5, and it is positively correlated when it's above 0.5. So this is the method we used many years in order to determine this roughness exponent, right? And to answer the question again, is there any information in these fluctuations of these residuals that we had at the beginning in the first two slides? Okay, good. Now we have a problem, okay? So people did this, and but notice soon there is a problem. What is the problem? I plotted here now artificially data with alpha of 0.5, which is just a random signal, with 0.7 and with 0.9. Okay, something that is more smooth. You see, this is more fluctuating, more rough. This is more smooth. So if you do now a moving average, this is the blue curve, a moving average, you see something very interesting. You see that you can identify certain patches in the signal as trends, right? You see this? I mean, here it goes up, right? Here it goes down, here it goes up. But this is not really a, it's not really a trend, you know? It's just because of the statistical properties of the data.
But isn't it a trend? Because it's correlated data. So
it's correlated data, but
so it's a real trend because it was up before. It's going up now. It's a
yes,
real
but the
phenomenon.
trend is something that is externally imposed on the signal, right? If it's just so, let's take global warming. Okay, what is the external trend? Then let's take world temperature. Okay, what is the external trend on the data? Going up, global warming. But if the data themselves are positively correlated, they will also have patches where they go up. Okay? So how do I know now, when I have a patch that is going up, that this is because just of the correlations in the data, the autocorrelations in the data, the memory in the data, or this is because of global warming, the external trend? I need to know this because I do climate models that predict how the temperature will be in 50 and 100 years. I need to distinguish these two things, right? So when I look at here the global temperature, which you see here, over from the 1880s to the 2000s, and you see the red line is the 5-year mean. So what here is really because of global warming, and what is the contribution just of such effects, that because of the correlations in the data we have increases that look like trends. That's the question. Okay. So here's another plot. Just interesting side notes. The side note is when you look at this. That was a couple of years ago, 10-15 years ago, was a big discussion among these climate skeptics, right? Skeptics, they say, look, here in the 40s, the global temperature decreased by a significant amount. So this is a indication that CO2 does not cause warming, because if you remember from the beginning, the increase in CO2, it was going up continuously since the 1800s, right? And here they say, okay, we have an increase in CO2, and here we have over 10 years a decrease in temperature. Why is this?
Because the what?
They were busy in doing other things than measuring temperature, so it's just a matter of statistics, right? So they didn't measure at certain places because just there was nothing to measure, because everything was just destroyed. So this is clearly not an indication that CO2 is not causing global warming. Okay, but let's get back to the to our problem. And here another, maybe more drastic thing. Ethan, I want to. Ethan or Ethan?
Whatever you want.
So Ethan's comes one actually. So Ethan, I try to convince you. So again, you have here now you have 0.9 correlated data, okay, with alpha 0.9, and this is simulated temperature data over 200 years, okay, roughly. And you see, and now you would just do a linear fit, okay? The dashed line, linear fit, would tell you that there's no trend here. It's just when you would plot outside this window, it goes in the other direction, you know? So it's just to zoom in the 200 years and you get this picture, do a linear trend, regression, and you get here an increase in temperature from 0.5 increase in temperature over 200 years. Okay.
So you can only differentiate between the correlations and some other trend if they're on very different time scales. Right.
Yes, and we will learn about the way to also solve it differently, but in a minute. Or if you look at the last 40 years, look, what would be your regression? It would be an increase of more than 1 degree, right? And it's just statistics of the data. There's no trend beyond. So linear regression suggests trends would correspond to a warming of 4.5 degrees in 100 years. So this would be here the extreme example. So what we need is to automatically distinguish between external trends that we have because of global warming, so to say, and the kind of persistence in the data when just because of statistics, okay? And there is a method that is an improved version of the fluctuation analysis. It's called detrended fluctuation analysis, and there will be a lecture by Ravid who will tell you exactly how to apply DFA to take out trends, to distinguish trends and persistence, right? But I don't want to tell you more because it will be boring when you hear him. Afterward, it will be too much redundancy. Will be too much redundant. But let's just assume we have this method, okay? That we can apply it. So so we learned about the roughness exponent, Hurst method to calculate roughness exponent. We said, okay, Hurst method we don't use anymore, we use fluctuation analysis. Fluctuation analysis has this problem now that we have patches in the data that look like trends, and maybe we also have trends in the data that don't distinguish between the two, and we need a method that can distinguish between the two, which is the detrended fluctuation analysis. Let's keep it there for the sake of the methods, and just talk again, kind of a summary about all the things that can happen in our time series and how we can, how we deal with this. So if we have non-stationary time series, mean and variance are not constant. So we saw the example of temperature data with seasonal trends. Temperature data, CO2 data, we had seasonal trends, right? And we said, okay, how can we get rid of it? We just subtract the seasonal cycle. Okay, very easy. If we have jumps in the mean, for example, what we saw with these heartbeats, we had their jumps going from we were asleep and then we are awake, so we have jumps. This makes it non-stationary. How would we solve this? We just we look at patches of data where the jumps do not happen, right? This way we make it also stationary. If we just look at the sleep stages themselves, we just analyze everything during deep sleep, it's more or less stationary, the heartbeat. If we just look at light sleep, more or less stationary, so we kind of divide the time series in stationary windows, which are the sleep stages. Now we have this slow increase or decrease that is externally driven, like global warming, or when you have urbanization in a temperature series. So urbanization means you in a city you always have higher temperature than in a village, right? Because of just more houses, more warming, and so on. So in order to remove this kind of trends, we need DFA that Ravid will talk about. And if you have very strong persistence, we can also deal with this with DFA. And you can also have apply this kind of segmentation, but the segmentation is just dividing the time series in stationary windows. This would be more done manually, and the segmentation is something more automatic. Good. So if you now apply DFA. Okay, so you take out the trends, you simply or calculate pure correlations in the data, autocorrelations in the data for different time series, then you obtain the following picture. Let's look first at the water level in rivers or river runoff data. You see in here on the x-axis, you see the different levels of correlations or alpha values, 0.5 to 1, right? 1 is very smooth and 0.5 is random. And you have here rivers in Bavaria and Germany compared to international rivers. And what you see is it's not universal, right? You have rivers where the water level is more or less random, okay? And you have rivers where it is very much correlated. But there's no pattern, so to say, in the data. It can be random, it can be positively correlated, not universal. Let's look at precipitation. What is precipitation? English word? Yes, it's rain, rainfall. Rain and snowfall. Okay, rain and snowfall. What do we see? Somebody can, I mean, it's already written there. So, yes, no. So rainfall is random. Okay, rainfall, the amount of rainfall is random. It's about 0.5 and it's universal. No matter if you look at a highland, inland, on the coast or island, it's more or less random. Okay?
Universal, like it's the average rainfall all around the world?
No, you go at different places in the world and there's no statistical difference in how the rain falls in the rainforest and how the rain falls in North America and in Thailand, you know.
Okay. So every climate is exactly.
Yeah, every climate
is expected exactly the same precipitation.
Yes, rainfall is behaving the same.
Yeah. Okay.
Random. Okay. Let's go to the temperature because this is what we started our discussion with. What do we see for temperature? We see that it is universal, right? It's universal. It is not random because then we would have a peak here. It is long-term correlated. Positively long-term correlated. Why is it positively long-term correlated? Temperature?
Because of the pressure.
Yeah, I just told you before. It's the high pressure and low pressure areas, right? So they lead to a universal kind of positive correlation around 0.65. Not as strong as I showed you in the example, right? The example was exaggerated with 0.9, where we had this 4.5 degrees trend. No, it's around 0.65. But it has to be taken into account when you do climate models. When you want to predict temperature in 50 years, this is an effect. You have to consider it, right? This is about over land, okay? Temperature over land. This is the temperature over the oceans. Sea surface temperature. What do we see here?
Big correlation.
Also universal.
Very spread out, not universal.
Yeah, it's okay. It's less universal than this and more universal than this. Okay, let's say it like this. It's centered around 0.8. Why? It is higher than land when you measure these correlations over water. Shear, any idea why it is higher over water?
Because the capacity of heat.
Heat capacity. Water has a higher heat capacity than land. Okay? When it is already very cold in the desert overnight, you're in Mitzvah in the night, in the summer, it's very cold there, right? But if you sit in your car and you go to Tel Aviv, you can still jump into the Mediterranean and it's warm there. Okay, it's also warm in Tel Aviv, but you get the point, right? It's the heat capacity of water. This is why, and this comes in addition to the high pressure fields. That's why you have higher correlation. Okay, and this is just what I told you about these climate models, that you have to first, earlier models from the Max Planck Institute, they didn't take into account this correlation effect. And then there was a line of research where people pointed to this effect, and now it is taken into account almost entirely across all climate models. Good, so we finished the first part of the class answering the question whether in these residuals there is any information, right? And we said yes, it could be random, it could be correlated, the noise could be correlated, and we can apply fluctuation analysis or detrended fluctuation analysis to decide whether it has any useful information, right? So this was the first part of the talk. The second part of the talk is now that we want to identify dominant frequencies in the time series. Okay, and this most of it you probably already know, but just for just to give the full picture, I mean, Fourier analysis is able to kind of determine what frequency content you have in time series. You are familiar with Fourier transform and inverse Fourier transform. Basically, what the Fourier transform is, it is representing your g of t, okay, or your time series as a integral of complex exponentials or mixture of sine and cosine functions, right? And when you look at this GF, the Fourier transforms, okay, GF is the Fourier transform of g of t. So, and g of f has an amplitude spectrum, and it has information about the phase, right? And you get the information about the amplitude simply by doing kind of Pythagoras, right? You have a real component, you have an imaginary component, you square them, you take the square root, and you get the amplitude spectrum. And the phase spectrum, you just get, imagine you have the phasor and the two-dimensional imaginary plane, and then it's just the angle, right? It's the angle between what you have on the imaginary axis and the real axis. So when you look at time series, then you typically don't have a continuous function, g of t or h of t, but it is sampled at equidistantly at time intervals delta t. So you sample, instead of ht, you sample hn, when n is going from minus infinity to plus infinity. In mathematical sense, in the physics sense, you go from 0 to infinity or until the end of your experiment. And what you have in what you also have is a critical frequency. So this is the critical frequency, and it is precisely 1/2 of the sampling frequency, or 1 divided by 2 times this sample interval, this time interval, right? It's called Nyquist critical frequency. So basically what it means is that if you sample a signal at a rate of 2 Hertz, okay, which would have a delta of 1 divided by 2, 0.5 seconds, you can only detect frequencies in this signal of 1 Hertz, 1/2, right, of this. Or, in other words, if you want to measure or detect a sine wave of 1 Hertz, you have to sample at least 2 times. You have to get at least maximum and minimum, for example, right, in order to identify it as a sine wave. How does this look familiar to you? I mean, if you think about 1 divided, so you have f equal to 1 divided by 2 times delta. What does it look similar to? Put just multiply f times delta, and it's 1/2.
Uncertainty principle.
It's an uncertainty principle. From where does the uncertainty principle come from?
Fourier transform.
It's, yeah, and the Fourier transform is basically you're taking advantage of wave properties, right? So this is basically just the uncertainty principle, and it comes from the wave property of in quantum mechanics we have the wave function, right? And here we have sine and cosine functions. And if you want to learn a little bit more about this, there's a nice YouTube video from Sabine that explains this quite nicely, to my opinion. You can check it out. It takes too long to watch it now. Yes, okay, a couple of things that follow out of a Fourier transform. So we said, since we have discretely sampled time series, so we need to look at the measurements at time points tk. Tk is k times the sample interval. K is going from 0 until n-2. We said we have a critical frequency, that the maximum frequency that we can detect in the signal, which is 1 divided by 2 times delta. And now we can also determine the frequency bins, right? The frequencies that we can calculate for our data. So you do this here with Fn is equal to n divided by the length of the time series times the delta times delta. And with this you can just approximate the integral. Right, the integral into a sum. I mean, you have discretely sampled measurements, and you end up with the Fourier coefficient. So basically, what you are doing when you do a discrete Fourier transform, you calculate your frequency bins. Okay, these are the Fn's, and then you calculate how much intensity you have in each of these frequency bins. And this is your Hn, your Fourier coefficients, so to say. Good. It's very, this whole framework is very powerful because of two very important properties. First of all, this Hn is periodic in n with the periodicity of the length of the data. So this makes it easier that h of minus n is equal to h capital N minus small n, and also Hn is equal to the complex conjugate of itself. Okay, so this is also very handy, and this leads to you just looking at the Fourier coefficients from 0 until the Nyquist frequency, basically.
Isn't the second property only if the data is real or something?
Yeah, it has to be real. Yeah. But we are physics people. So that's usually happening. Good. Let's look at an example. Stump example. A time series that has 10 Hertz, 25, 50, and 100 Hertz. Okay. You mix it together, you get something like this. Okay. You do a Fourier transform, and you get, surprise, surprise, a peak at 10, 25, 50, and 100. Simple task. Even my daughter could do this, 12 years old. Question for you, what is the sampling frequency here? Always need to sample this data. Okay? What is the sampling frequency?
It needs to be a minimum of 200 to catch the last thing.
Yeah, but if you see a plot like this, we said the plot is always shown between 0 and Nyquist frequency, right?
Oh, so 400.
So it's 400, right? So the this is always sampling frequency half. Now I take the same signal as before. What is the sampling frequency? 160. Oh. I have 10 Hertz, 25, 50, 100, and it's at 60. What happens?
Because the 100 is too big for 160 to catch.
So what happens? Yeah, actually 100 is here, right? And I cannot, I violate the sampling theorem, which says I need to sample at least twice the frequency in order to catch this frequency. I violated this. I didn't sample with 200. I sampled only 160. So what happened?
Wrapped around to 60.
It is folded inside, right? I mean, this is supposed to be here at 80 plus 20, and it appears at 80 minus 20. Okay. So this is called aliasing. Here, aliasing. Okay. And that's important to be aware of when you do experiments, right? You don't sample high enough your data, this can happen, and then you report a frequency that is actually not present in the data, just because of too low sampling. Another thing is actually a problem with Fourier transform is that it does not preserve the information in time of time. I mean, you can see, I mean, you do an integral over t, so you lose all time information, right? If you have a signal, let's take a signal like this that has a low frequency in the beginning and it finishes with a high frequency. When I do a Fourier transform of this and I calculate the power spectrum, then I get all the frequencies, 10, 25, 50, and 100. However, I don't know when they happen, right? Because I consider the whole duration, and I lose the information about when what happens. Any idea how to solve this? Very easy solution to it. You just do a Fourier transform in windows, right? You calculate your Fourier transform in a window here, then in this window, then in this window, and then you obtain the right frequencies. You take the first window, you get your 10 Hertz, 25 Hertz, 50, and in the last window you can see here it's 100 Hertz. Okay, windowed Fourier transform was logically the next step that they did in order to get the time information of what happens in the time series. And when you do this more sophisticated, this windowed Fourier transform, you obtain this kind of spectrograms. So if you look at this signal here, it starts with white noise, I mean random, and then you have some increase in amplitude, but still white noise, and then you have a characteristic oscillating behavior there. And now what you do is you calculate here over the same time axis. You see it's the same time axis. You calculate a windowed Fourier transform, but instead of showing these bars that I showed you before, right? So here I showed you these bars going up, so it's this three-dimensional picture. I do a color code, right? I do a color code and I color it to brighter and brighter colors when I have a higher intensity. So when you look here, there's nothing going on until 20, basically. It's white noise. All the frequencies are equally contributing to the signal. Then you have an increase in amplitude, so you have so these are basically the frequencies that contribute to this signal. It's not really white noise, but it still has a broad frequency content. And then you come to around 30, and you see that the dominant frequency here is around 5 Hertz. Right? See here, 5 Hertz. So this is 5 Hertz, and then afterwards it becomes again something more random. So this is one way to determine different frequencies in the data. And another one I wanted to mention, more elegant, and something that was when I was your age, they started to develop this theory in mathematics, and it's called wavelet transform. So what we will do in the wavelet transform, for the Fourier transform, we said you try to map everything on sine and cosine functions, right? This was the idea behind the Fourier transform. For a wavelet transform, you do not fix yourself on sine and cosine waves, but you say my underlying function is a wavelet. It can have whatever geometry, okay, it can look however I want it should look like. However, it has to have two properties. One property is that the integral you can, the square you can integrate. So you can do an integral of the square of your mother wavelet, and you can normalize it. Okay, these are the two conditions. And examples are the simplest wavelet is the Haar wavelet. This is just like a Heaviside function. Okay, and Mexican head wavelet. So it looks like Mexican head. Yes, so it's the third derivative of the Gaussian. Okay.
Is the left one periodic, or does it just stop when it becomes zero?
No, this is the wavelet. It's not periodic. This is this wavelet. Okay. But now comes the thing. Well, not now, but later. I just show you some pretty pictures before what you can do with it. So now, what you are doing is you plot again these spectrograms. Okay. The spectrograms, but what you do with, let's take the Mexican head wavelet, you can stretch it, or what's the opposite of stretch? Shrink?
Shorten.
Yeah, shorten.
Squeeze it.
Squeeze it.
Yeah.
Okay, so you can make it bigger and smaller, right? And this is the scale. If it is smaller, you look at more fine details of the time series. So you get every little bump here in the signal. Okay, and this is what you see in the first line. So you get, when you translate it into frequencies, what do you get when you make it very small? High frequencies. Okay, and when you make it very big, you get low frequencies. Okay, good. So we understood this. The scale of the head, for example, goes from small heads, from small scales to from small scales to large scales, and the frequencies that are detected by this are high frequencies and low frequencies. Okay, so this is what you have to understand first, and then how do you get here the time information? It's because you shift. So once you decided on the scale, so you say my Mexican head is this scale. Now you shift it over your time series. Okay, you shift it over your time series. In the next step, you take a bigger one, a bigger head, and again you shift it over the time series, and you calculate kind of the convolution between your head and time series. Okay? And when you have a big deviation between the head and the signal, you get here a dark color, and when it matches very well the signal, you get a bright color. Okay? Now let's go to the signal. Here we have something that is not very interesting. You also don't see anything interesting going on in the spectrogram. However, here now we get a low frequency, right? Low frequency signal matches very well in this area. It matches very well the wavelet, and then the frequency increases, right? Frequency increases means I go to smaller and smaller scales, right? Smaller and smaller scales until it gets again kind of noisy, and then I lose everything. And here I get a nice information about what's going on in the data. I could have done this also with Fourier transform, okay? But if I would have chosen something that does not look like a sine wave, then the wavelet would give you more information. Good, so I just explained you how to apply this wavelet transform. This is the formula. Basically, you take your mother wavelet, okay, this is your mother wavelet, and you scale your mother wavelet by this a0 to the power minus n. This just gives you the width of the wavelet, and minus n b0 shifts it through the time series. Okay, that's the whole secret behind wavelet transform. And here you have several examples. You have a small scale in black, medium, and a large scale, and here you have this location parameter that shifts it through your time series. And I just want to show this picture because I like it very much. It's a wavelet transform of an ECG. Okay, ECG, everybody knows. You have a QRS complex that corresponds to the depolarization of your heart muscle, after which it starts to contract, right? It doesn't contract all at once. It's like the heart muscle is pumping blood like you are squeezing a towel. Okay? It starts with the atria on the top, and then it goes down to the ventricle. So it makes a movement like this. So yeah, anyway, you get this kind of characteristic signal with clear peaks, and now we start again to apply a wavelet. I don't remember, it was not a simple wavelet, it was a more complicated wavelet, but it doesn't matter. What you do is you look at the signal at a low scale, right? Very narrow, so to say, head. If you take a head. So what you see here, you can detect each of these peak, right? Each of these peak. So you get information, microscopic information of the signal. Okay. Then you go to higher and higher scales, and what you see is here you see, for example, the average heartbeat. Okay, that it's around 1 second. So this information you would not get from the Fourier transform. So you see here the very microscopic information, and here you see some more macroscopic information. And when you go to larger and larger scales, so now it's just too short, but if you would imagine you have here 24, 48, 72 hours data, then you would get at a lower band, you would get information about the circadian rhythm, okay, or sleep stages. So it's a very powerful method where you can get a lot of information about all scales that correspond to biorhythms.
So why can't you get this with the regular Fourier transform?
Because you have this, your signal, the Fourier transform is only good when your signal looks more sinusoidal, okay? And it resembles more or less a sine wave. As soon as you get something that doesn't look so, doesn't look nicely like a sine wave, then you will get more artifacts in the data, right?
Why? But each frequency represents a single sine wave and ignores all the rest of the artifact.
Yeah, so let's do ECG with Fourier transforms. Who wants to do it? Yeah. No, I haven't done it, but I mean, once I did it, but I remember it looked very ugly. It didn't look so nicely that you have here clearly the peaks. It was more fuzzy because you try to So what happens when you have this large, what is the Fourier transform of the delta function? It's more like a delta function. So you get some flat, so you would get here not a nice peak, but you get something flat, you know, and I don't know.
So Ronnie, actually, when we studied today, we had like fields, electromagnetic fields,
Yes.
and I set in the exercise, and I thought maybe I can do something like this with the magnetic matter in the Firefox,
Yes.
and then from the magnetic matter you can extract the electric field.
Yes.
But I discussed it with ChatGPT, and he told me that the magnetic field of the heart is very, very small. It's like
Yes.
nano Tesla,
Yeah.
so we can't really measure
Yeah.
it.
It's
So, but it's interesting to do.
you can measure it, but not with the phone. I mean,
No.
that's the same problem when you want to measure electrical electrical activity in the brain is relatively easy, so everybody can handle an EEG. It's very easy. But if you want to measure the magnetic field, you have to. There's one lab in whole Israel that can do it, and we have it here in right.
We've been there.
Of course, yeah. So magnetic field
Huge
is
helmet.
right. You need huge helmet, and it's not so trivial. Magnetic fields. It's theoretically alright, but it's too low, and the phone would not do it. Okay, so let's wrap it up. Today we learned about autocorrelations and discriminated between random and correlated data, autocorrelation, fluctuation function, and DFA. And autocorrelation function I didn't talk about because also Ravid will talk about it. And we looked at frequencies and time series. We discussed Fourier and wavelet. Next time we are going to talk about phase information in time series and amplitude information. The analytic signal approach we will discuss, where we need the Hilbert transform, and we will study pairwise interactions by means of phase synchronization. Good. Any questions? Then thank you very much, and see you next week.
Thank you.
And Etan sent me your notebook.
Yeah.
So here I looked at your data, very nice. Now you have a lot of
Look, but I didn't understand. Here he's taking it to the Z acceleration, right? And then the Rpx here is fitting it in Fourier transform for the frequencies of the heart. Yeah.
afterwards. So look,
No,
Like I tried it now. Get some
no.
more. See, but I think it's